So here we are with our first topic for exam number 2, which is gonna be like molecular structures, molecular geometry, and everything can be summarized into this one acronym, Vsepr. Now, Vsepr, that's just basically talking about like what kinds of structures can you have? What are these things polar? Are they non-polar? How does this like help us identify what kinds of molecules they are? So with Vsepr 3, we need to I think this is the first slide. I'll just be going through her slides and trying to like talk through them. And so the first slide says molecular geometry. Molecular geometry specifies the positions of the atoms in terms of bond length and bond angle. So the shapes of the molecules and their orientation critically affect their reactions, especially for biological reactions where molecules must often fit precisely into their receptors. A molecule adopts the shape that has the lowest potential energy. And low potential energy means that it's more stable there, it's at its happy spot, and it's not always in this like high energy position. And then like, you know, that's kind of like saying it's pretty much why atoms have bonds with each other, because they want to reach like a lower energy state. But that's for a different video. I am getting off track. So Vsepr theory, molecular geometry can be represented by different models. Perspective drawing, which is like you have maybe like CH4, right? So then the perspective drawing is going to be, hey, these are all on one plane, but then there's this one hydrogen that sticks out. And you draw like a wedge here. And so it kind of like you see that it kind of gives you this three-dimensional feeling, and so that's going to be a perspective drawing. The ball and stick drawing is more like 3D, where you have these like the bonds represented by these little rod things, and you have each of the atoms represented by these little balls. So I know I drew it kind of weird, but it's pretty much the same concept. And then the space filling one, the space filling drawings don't show these rods, and instead they look kind of like it's a chevron version of a molecule. So they kind of look like that. So this here is this, and these 4 things are the hydrogens. And so those are the 3 ways that you can like draw molecules when you need to draw them. And you will need to draw them a lot, especially for like this particular topic, because since it is Vsepr, we're looking at atoms in relation to one another when we're looking at these kind of molecules. So Vsepr stands for valence shell, electron, pair, repulsion. And it simply is just a model for predicting your molecular geometry. Vsepr only applies to one atom at a time, usually the central atom. So the assumption or basis of Vsepr is that a molecule minimizes the repulsive force between electron pairs, so that it doesn't have as much potential energy, so that it can be like more low energy and just kind of chill. They will be as far apart on a sphere as possible to maintain the lowest PE. And so, for example, like CH4, these hydrogens are not gonna this hydrogen is not gonna swing over here and like be right next to that hydrogen, because then like all of their electrical forces, I guess, will repel them. And so they just like want a lot of space to like move around in. So this hydrogen is going to space itself as much as possible from the other hydrogens and vice versa. So Vsepr theory, number one, draw the Lewis structure of the model. When we're talking about molecular geometry, you can't just start from nothing. You do have to look at like, different aspects of the molecule first. And the first aspect is going to be Lewis structure. Number two, determine the steric number. The steric number is basically something that will help you determine what kind of molecule you're looking at, I want to say. So the steric number is the number of, that's not right. Okay. Steric number is the number of atoms that are bonded plus the lone pairs. And I'll show you how to do that later. Oh, by the way, I'll just like keep a count here on which video it is. Video 1. So double and triple bonded atoms count the same as single bonded atoms for steric numbers. So whether or not you have a double bond, a triple bond, or a single bond, those bonds are just basically like, it doesn't matter when you're looking at steric number. But steric number, I'll just like show you what it is. Steric number is like how many areas of electron density that you have. And so when in relation to this carbon molecule, or carbon atom, you have 4 different electron like densities. So if you look at where exactly the electrons are in relation to the carbon, you're gonna have like here, 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 and here. It doesn't matter how many electrons there are, it's just in relation to carbon. If I am carbon, I'm seeing 4 different areas where it's like, oh, I've got electrons here. So that's basically steric number, where you're looking at different areas of electron density. Okay, so the third one is determine the electron pair geometry. And then determine the molecular geometry. And you'll see exactly why later when I try to do like the problems, but when you want to get to molecular geometry, you have to like build up to it. You can't just like, I guess you could just go into it, but it's a lot easier if you like redraw it a few times. And the electron pair geometry, this is like, electric pair, electron. This is just basically molecular geometry except for the lone pairs. So when you have, because molecular geometry, that basically accounts for the fact that you have lone pairs that actually repel these things like farther. They have more repulsive, lone pairs have more repulsive force than just like bonds. Okay, so I'm gonna move on to the next slide, and I'm gonna start like showing you exactly what each step does. So when we're looking at steric number, we're looking at steric number because we want to know what kind of structure that we're looking at. So here's what she says on the slide. These are the geometries for the distribution of electron pairs for different steric numbers. They are not molecular geometries. They are the first step in determining molecular geometries. And so if you have a steric number of 2, you're going to have a linear structure. So if you have a central atom here, and then you have electron densities here, this is linear. If you have steric number of 2, or 3, sorry, you're gonna have trigonal planar. Trigonal planar. And that's basically where you have a central atom and 3 different electron densities, like this, but it's just flat. Like, that's their optimal place. That's where they like to chill. It's just flat all around. And then steric number 4, that's tetrahedral. And tetrahedral looks something like this, where you have the central atom, electron density here, and then kind of like a tripod. It has like this. So it's kind of like if you put it in a box. Yeah. So I don't know if that like helps you like look at it better, but it's just basically these 4 electron densities, because we have a steric number of 4, and it's kind of a tripod shape. And then I'll just come up here. Steric number 5, you're gonna have trigonal pyramidal. Trigonal pyramidal, it's like you have, this drawing's weird. From here to here, from there to there. Okay, I think I get it. So it's like you have like tetrahedral, except 2 of them stacked together, and this is no longer a tripod, but it's like a flat surface. And so you have kind of like a diamond shape, I want to say. So like you have a pyramid here, right? But then you copy paste it and then you turn it upside down and combine it. And so it kind of looks like that. And you look at it. But then like, this is just like the overall, hey, this is kind of how it looks. But the actual molecular geometry of it, molecular shape of it is that you have like the central atom in the middle, and then you have electron densities pointing straight up and pointing straight down, and then you have electron densities at each of these little vertices. So you have one here, and one here, and the distance between them, this is 120 degrees, which tells us that these 3 electron densities are all on like the same plane. Because when you look at, like, for example, a circle, right, you're gonna have 360 degrees. If you have 3 different electron densities like this, then this is your central atom. So I'm kind of looking at it from like an eagle's eye view, like from top to bottom. So these 3 are kind of stacked in my view. And so if these have an angle of 120, then they all must be on the same plane, because 120 times 3, 1, 2, 3, is 360. And if you look at it from a side view, where you're looking at like the central atom, these three different electron densities, and then the 2, one above, one below, then these are going to be straight up and down, and these electron densities are going to have a 90-degree angle with this plane here, like that. So that's trigonal, bipyramidal. Which makes sense because you have two pyramids, right? You have two pyramids combined with each other. So that's kind of how that looks. And then the steric number of 6 is going to give you an octahedral structure. An octahedral is, kind of looks like, so it's exactly like this, except instead of having 3 electron densities on this particular plane, you're going to have 4. And so it's like that. So you have like a plane here. Here's the central atom. Here's an electron density, electron density, electron density, electron density. Then you have one pointing straight up. And then one pointing straight down. So 1, 2, 3, 4, 5, 6. Steric number of 6. It's octahedral because you have like this kind of shape here, which is just basically that except 4 on this plane. So everything in this particular shape is a 90-degree angle, because when you have like 360 degrees, then you have 4 electron densities pointing out like that. What's 360 divided by 4? That's going to be 90. So yeah, and then here I'll give you all the different angles for these. So if you have a steric number of 2, linear, this is 180 degrees, so is that one. When you have a trigonal planar, then you have 120 degrees here, and then 100 here, 120 here, 120 here. When we have a tetrahedral, you have 109.47 degrees in between each one, 109.5 degrees, 109.5, 109.5, 109.5. That's like basically how you memorize it. Just gonna keep saying 109.5. So within a tetrahedral, you have 109.5, 109.5, 109.5, 109.5, 109.5. So on and so on and so forth. That's like pretty much how people are memorizing it, I think. I don't know. But apparently you kind of need to know the angles, so I would like remember them just to be safe. Steric number 5, trigonal bipyramidal, 2 pyramids on top of each other, trigonal, like triangle, kind of like triangle plane here, like this. You have 3 here. That's going to be 120 degrees in between each electron density. One up, one down. So when you have a plane and something sticking right like up and down to it, that's going to be a 90-degree angle here. For the octahedral, everything is 90-degree angles, because when you have like electron densities like that, then you have 90 degrees here, 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 and here. Up, down, that's going to be also 90 degrees. Okay. So those are that's kind of like a quick overview of like electron geometry. And now to start with molecular geometry. I'll like cover that in the next video. I want to show me just wiping down the board.